Before we start, let me introduce myself. My name is Piotr Stepian. I'm working in midas IT as the technical support engineer. And during this session, I will remind you some knowledge from the nonlinear static analysis and linear dynamic as well. But the main focus will be put on the nonlinear dynamic events, or let's say short-time events. At the end of today's webinar, there will be some time for questions, so I would like to invite you to use the chat section in your GoToWebinar panels. So of course you can ask during the webinar and we will try to answer all of them live. My colleagues, Mr. Cyprian Russo and Apur Sharma will answer your questions. And if we want, we will collect all your queries and we will back to them later. So let's start the webinar. Let's start from the dynamic analysis overview. The graph which has been presented on the screen defines what should be provided when we want to perform dynamic study and what kind of output we can expect. So the main reason to perform any kind of dynamic analysis is your structure when your structure is subjected to non-constant loading, which could be defined in time or let's say frequency domain. So there is a need to specify a dynamic load. So our structure should also include the information about the mass and the stiffness, and this is realized by material and property definition. So these two parameters should be always present in your structure or in your system. So how does a structure will behave under an input load and what kind of response can we expect? So answer on these questions defines the required type of analysis. So we have to study first what are our modeling assumptions and let's say modeling conditions to select the proper type of the analysis. So we can choose between the transient response analysis, frequency response analysis, response spectrum, and random. And the most popular output is response as velocity, acceleration, and displacement characteristics. And today, the main focus on today's webinar will be put on the nonlinear transient dynamic analysis. So what tool should I use? This is the question if I want to analyze a nonlinear dynamic problem. So the answer exactly lies in the name, and right now I would like to explain to you the meaning of every word in this title. So first of all, let's refresh some knowledge from nonlinear static analysis, and let's define the term which is called nonlinearity. So there are three types of nonlinearity you can meet during your FEA simulation. First type is the material nonlinearity, and this refers to the material behavior above, let's say, the proportional limit of the stress-strain curve. Second type of the nonlinearity is the contact, and this refers to the topics like large deformation, large rotation, and follower forces. So if you want to consider these effects, the contact is the feature that you use. And the last, actually, excuse me, it was not the contact nonlinearity, it was geometric nonlinearity, which refers to this large deformation, large rotation, follower forces. Sorry about that. So this is the geometric. And the last type is the contact, which will be important when we want to analyze response in assemblies or when let's say there is a need to assign more advanced boundary conditions. So the term transient defines the type of analysis and response and related output. So transient analysis for nonlinear problems is performed in the time domain. And these both terms, which are implicit and explicit, refer to two types of time integration methods which are used to perform calculations. So we will talk about this algorithms. And finally, we have the term which is called dynamics, and this refers to the inertia and mass-related effects in your system or structure. So when those two factors play an important role for the response, the dynamic analysis is the right choice. In midas NFX, material nonlinearity can be provided via elastoplastic and hyperelastic model. Elastoplastic model takes into account the plastic hardening phenomena, and this hardening is defined, or let's say described, via stress-strain curves. And the second type for the elastoplastic model is the perfect plastic. So when the plastic limit in your material behavior is reached, there is no hardening and we can observe the plasticity. The second model is the hyperelastic material, which is still an elastic material, and this means that let's say the specimen will return to its original shape after the force have been removed. So the difference to the linear elastic material is that in hyperelastic the stress-strain relationship derives from a strain density function. And as the example, often elastomers like rubbers are modeled using hyperelasticity because usually they have large strains at the small loads. So this type of material is nearly incompressible, and what you should remember, the Poisson's ratio is very close to 0.5. And midas NFX supports following hyperelastic material laws like Neo-Hookean, which is the most simple approach, Monet-Riplin, polynomial, Blasko, and Oddgen. Stress and strain curve is used to describe the nonlinear behavior of the material. So this curve is sometimes named as monotonic curve, and tension stress strain properties are usually reported in many handbooks, and they are used in many specifications. So this material behavior, as you see on the screen, is obtained from a simple tension test, where a specimen, let's say with circular or rectangular cross-section within the uniform gauge length, is subjected to monotonically increasing tensile force until it fractures. So if we take a look on the picture again, we see that curve is subdivided into 4 sections. So the first section to the left refers to the linear region, and in this range the Hooke's law is valid. And as you see, there is a proportional relationship between the stress and strain. Next section defines the perfect plasticity. The next region is related to the hardening, and the last one refers to the fracture. So you have to also remember that the most popular material stress-strain data are provided as engineering data. So curve on black color represents the engineering curve, but for the simulation, the more valid approach is to input the true stress-strain data. So how to create the true stress-strain curve? It's very simple when you use presented formulas. So on the slide, we see the example of the data conversion. So there is a table with engineering information and true stress-strains data. So using these formulas, which are valid up to necking only, you have to remember that, you can easily convert this data. So this is a very important assumption. Now let's talk a little bit about the contact nonlinearity in your dynamic simulations. So as I mentioned before, the contacts are used to describe the behavior and relationship between the parts of your assembly. So in NFX we have three types of contact definitions. First one is called surface-to-surface contact and is suitable for cases in which the structure of an object penetrates into another object. There is a need to define the master and slave segments for the surfaces being in the contact path because they are determining the direction of the contact elements. So this type of contact is commonly used when the contact area of the, let's say, contacting surfaces is relatively large. The second type, which is node to surface contact, is used for the cases in which the slave segment penetrates into the master segment only, and this causes, let's say, increase of analysis because only one direction, increase speed of the analysis because only one direction is checked for searching the contact. So it's used for the cases in which contact area is relatively small, and it's also possible to predict the location when the contact would occur. And finally, the last one, self-contact. This type of contact definition will recognize all elements which comes from the part itself. This will be done automatically, and next it will generate the contact elements or contact connections. Self-contact is used effectively when it's difficult to predict where the contact would occur due to the a large deformation. Another important terminology which is related to the contact nonlinearity describes the penetration level between the surfaces being in contact. So generally speaking, we differentiate four categories for the behavior of contact type in two directions for the contacting surfaces, in the normal direction and in tangent direction. So if you take a look on the table, let's start from the general penetration type. So general contact allows separation and sliding with resistance proportional to user-defined coefficient of friction. The second type, welded, there is not possible to penetrate, separate contacting elements. There is also no sliding. In bidirectional model, the behavior is similar to welded, except that there is no friction and sliding can occur. Finally, roof, which is totally opposite to bidirectional sliding. In this model, separation is allowed, but there is no sliding, and sometimes this behavior is called as, let's say, contact with infinite friction. And from this slide, I would like to start to talk about the type of the dynamic analysis which are available in midas NFX. So this refers to the nonlinear dynamic analysis. And at this moment, it's very important to say a few words about the main dynamic equation and basic concept of its solution methodology, which refer to the numerical time integration. So the equation presented on the top is the one which is being solved during the analysis, and I'm sure that you remember this from the high school of the college. And this equation, let's say, is created or assembled for every single degree of freedom in your model. And if you take a look on the letters in this equation, M defines the mass matrix, A stands for acceleration vector, C describes the damping matrix, V is the velocity vector, K is the stiffness matrix, and X is the displacement vector. And to the right we see a force vector. So as I said before, the transient analysis is the one which refers to the time-dependent events. So every equation for every single degree of freedom in your system will be integrated in time to provide you the information about the response of the system. And the total response of your system is defined as the sum of particular equations at incremental time steps. And from now, our concern will be how this process will be performed. I mean the process of the time integration. So implicit and explicit are the methods, or let's say they are approaches which are used in numerical analysis for obtaining numerical solutions of time-dependent ordinary and partial differential equations, as is required in computer simulations. So this is the method. And implicit methods find a solution by solving an equation involving both the current state of the system and the later one, while the explicit methods calculate the state of a system at a later time from the state of the system at the current time. This is the main difference. And implicit time integration focus on displacement by inversion of stiffness matrix. And this process, this inversion of the stiffness matrix, is a huge task for your CPU and for memory. Also, the feature of this method is that average accelerations and displacements are calculated over the time steps. Explicit time integration focus on acceleration by inversion of the mass matrix. So in the first type we have inversion of stiffness matrix, in the second method we have inversion of mass matrix. And usually the masses are lumped and the mass matrix becomes a diagonal matrix. And this is very easy to perform by your CPU. And from here we can explicitly define the time and calculate the velocity and then displacement. So now let's talk a while about the numerical stability of the solutions, because this is a very important term. And I would like to give you some short introduction. So this term comes from the numerical algorithm and refers to a desirable property of numerical algorithm. And the precise definition of stability depends on the context, but it's derived from the accuracy of the algorithm. So sometimes a single calculation can be achieved in several ways, all of which are algebraically equivalent in terms of ideal real or complex numbers, but in practice, when performed on digital computers, yield different results. So some calculations might dump out approximation errors that occur, others might magnify such errors. So calculations that can be proven not to magnify approximation errors are called numerically stable. And one of the common tasks of numerical analysis is to try to select algorithms which are robust, that is to say they have good numerical stability among other desirable properties. And according to above definition, both methods differ from each other. So implicit method is unconditionally stable, because of linear approximations, and in case of explicit, maximum critical time step exists, and to ensure the stability we need this critical step, and that's why the explicit method is conditionally stable. So implicit method, as I said, are usually unconditionally stable regardless of the size of the time step. So in explicit method, time step size must be chosen as a value smaller than the critical time step size. And this is the equation what you see, delta t equals to 0.85 delta t critical. And this 0.85, this is a global scaling factor, and sometimes you can meet the value of 0.9, and some codes are using this number. So generally it's not possible to determine the stability limit exactly, so some conservative estimates are used instead. And the stability limit has a great effect on reliability and accuracy, so it must be determined consistently and conservatively. So if we take a look on this critical time step size, the stability limit is defined in terms of the highest frequency in the system. So for the system without damping, we have this equation which equals 2 divided by maximum frequency, and the second equation is valid for the system when the damping is applied. So to ensure the stability and accuracy of the solution, the size of the time step used in explicit time integration is limited by the Courant criterion. So this condition implies that the time step is limited such that some, let's say, stress wave cannot travel further than the smallest characteristic element dimension in the mesh in a single time step. So thus the critical time step for the solution stability looks like following. So we have delta T critical equals to the L divided by C, where C is the wave propagation velocity, and this term is valid for the one-dimensional elements. As you see, there is no Poisson's ratio, for example. And the stiffer the material, the higher the wave speed, resulting in a smaller stability limit. So, for example, the time steps used for the explicit time integration will generally be much smaller than those used for the implicit time integration. So in example for the mesh with the characteristic dimension of 1 millimeter and material sound speed of the sound of 5,000 meters per second, the resulting stability time will be 0.18 microseconds, and to solve some simulation to a termination time of 1 second, you need more than 5,500,000 time steps. And you're supposed to also to take care every time when you are generating the meshes for explicit dynamic simulations to ensure that one or two other number of small elements don't control the time steps. But I will back to this topic a little bit later. So next slide shows the simplified calculation for wave propagation in two-dimensional elements. So for quadrilateral meshes, the characteristic dimension L equals to the area of the element divided by maximum edge length. For the triangular meshes, area is multiplied by 2 and then divided by maximum edge length. So speed of the sound will be estimated as the square root from Young's modulus divided by density multiplied by the term in the narrows. So as you see, Poisson's ratio is included. So for 3D elements, and in that case, in this example we see 3D hexahedron, the characteristic dimension L equals to volume, which is divided by the maximum side face area, and speed of the sound will be estimated in the similar way like to the elements. So generally speaking, hex-dominant meshing is preferred for explicit simulations because this algorithm computes dynamic stress waves that need to be accurately modeled as they propagate through the entire mesh. And this is why hexahedral mesh is more efficient, and we can also control the element size. So now let's summarize the implicit method in terms of practical usage. So first of all, implicit method, as we know, is unconditionally stable. We can use variable time step during the analysis, and as the additional information midas and fx has got an auto step option, which is very useful to control the time step automatically. Achieved solution is very accurate via the implicit method, but as we discussed previously, we have to pay for that because the solution requires the matrix inversion, which is computationally costly process. And this method is valid for long time duration dynamics, let's say, where the event time is relatively long and nonlinearity is, let's say, on the middle level. Explicit method inverses diagonal of the mass matrix instead of the stiffness matrix, and this makes the method computationally affordable for the calculations. And there is also no convergence criteria, so solution is achieved very quickly per each time step. But the method is conditionally stable, and once again this means that critical time step is important factor for the time stepping. And the graph on the next slide describes the great cost savings over the implicit method by the explicit as the model size increases, as long as the mesh is relatively uniform. So we see that influence of mesh refinement is very high for the analysis via implicit method for the computational effort. Implicit method is less sensitive, and CPU cost increases proportionally to the problem size. So when to use the explicit analysis? So once again I will refer to the time steps, and generally the time step for implicit, as you know right now, can be much larger, and this makes implicit methods more attractive for transient events that occur over a long time period and are dominated by low frequency structural dynamics. Explicit solutions are better for short transient events where the effects of the stress wave stress waves are important. So there is of course some area where both of the methods will be used and may be used. So for example, creep, hydroforming, slow deep drawing are the examples where the implicit algorithm will be sufficient, and for the explicit applications this method may be necessary for problems that include material nonlinearity, as we discussed before. So a high degree of material nonlinearity may require a small time step for the accuracy when you want to perform calculations with the large geometric nonlinearities. So some contact and friction algorithm can introduce potential instabilities, and small time step will be needed for the accuracy and stability, and so on. So you'll see that let's say less time problems are more valid for the explicit. So now I would like to give you some basic tips for better modeling using the explicit FEA. So in regard to wave propagation, it's always good to have smooth and clean, let's say, geometry of your elements. So you have to avoid the small distorted elements which can control the critical time steps. It will be good when you generate a uniform orthogonal mesh. I'm talking about the 3D meshing and 2D meshing. And in, let's say, keeping the critical element size close to the sheet metal thickness is also very important, and it's very best because it's very important to keep, let's say, the same proportions of your element. And now let's switch to the software, and let's make a few examples for implicit and explicit. Okay, so I prepared for you some examples, and we will start from the example of the simple drop test, and we will solve this problem via the implicit model. So what are we doing? So I will start from the material definition. So I'm clicking on the material and selecting the add and isotropic, and let's specify the elastic modulus. In our model W1.1 to the power of 11, because we are working in the Newton and meter as the unit. Poisson's ratio is 0.3, and as you expect, mass density will equal to 7,800. And let's change the name to steel, and let's click on OK. And we will use the same material definition for both geometries, this means for the plate and for the block as well. Okay, let's define the properties. So this model has been imported from MSC Nastran, and actually we don't have any information about the properties, and this information about element lies under undefined branch. So if I click on the define, I can change the thickness of the plate. So let's say the plate thickness is 2 millimeters. So let's change this to 2, and let's click on OK. And let's repeat the same for the block. And in that case, I don't have specify anything because we are working with the solids. So I'm clicking on OK. So I have the property, and if I click on this 2D, I can display the thickness, for example. Okay. And now let's go to the contacts, and via model info 3 I will add a contact pair to the system. So I'm clicking on the manual contact. So the contact type will be surface-to-surface contact. Penetration will be related to the general, and as the master I'm selecting all of the two-dimensional elements, and for the slave I will select all of faces, and I'm clicking OK. We can display the contact pair. So now we see master is colored on red and slave is colored by blue. Okay, so let's hide this contact pair, and right now via the ribbon bar I'm going to assign the constraints. So let's click on the top view and let's assign the boundary conditions to the plate. So I'm selecting the nodes from both ends and I'm clicking on the fixed button. Okay, I have it. And right now I'm going to specify the acting forces, and I'm starting from the gravity. So gravity will act on the zeta direction in the opposite side. So let's click on preview. So direction is fine, so I'm clicking OK. And let's define the initial velocity for the block. So to do that, I can use the ribbon bar and let's click this icon, initial velocity, and let's select all of the nodes from the block, and the value will be minus 0.1 meter per second. And let's change the dynamic load set to initial velocity, and let's click on OK. Okay, so my model is ready, and right now I'm going to specify the analysis parameters. So I'm clicking on analysis case, I'm clicking on other, let's add the title, and let's select the nonlinear implicit transient. So this is the transient where we start. Let's specify the subcase control settings. And first of all, I will create two subcases for that model. First subcase will be related to the free fall, and the second will provide us response after the impact. So this is the first subcase. Let's add the second one, and let's set up the first subcase. We can change the name if we press the F2 button. We can change the name to free fall, and let's do the same for the second subcase, and this will be impact. Okay, so let's click on the free fall and let's click on the subcase control. So first thing I'm always doing is checking the geometry nonlinear, and let's set up the time duration, and for my model it will be 0.2473. Let's correct this, and this is related to the height from the plate, so you can easily calculate this value, and the number of steps, of time steps, will be 10. Okay, and if we go to the additional load, there is one static load set which includes the gravity function. So I'm selecting this, and time function will be none, which means the gravity will be constant, and this will be the global attribute. Okay, so I have that. This means that the static load will be converted to the dynamic load. So I'm clicking OK. And let's assign the active loads and boundary conditions. So I will drop the initial velocity under proper branch. So this should be moved under this branch. And contacts are assigned, and we have to do the same for the second subcase. Okay, so right now I'm clicking on impact. I'm clicking on subcase control, the same. I'm checking the geometry nonlinear button, and the time duration for my response will equal to 1.1863 seconds, and the number of required time steps will equal to 300. And the same, we have to select the static load. Let's select the function and set the global time as the attribute. Okay, so let's click on OK. Let's assign the same boundary conditions, and there will be no initial velocity in the second set, so the manual contact is the one feature which is supposed to be defined. So now I'm clicking OK, and let's start the calculations. I'm clicking on solve, and now we see the interactive graph, and as you see that this is the maximum displacement versus the global time. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Actually, we don't see the previous steps at this moment, but this refers to the first subcase, and now we are observing the solution from the second subcase. So let's wait a few seconds. Now we have 5% of the solution. So at the bottom of the software you see the monitor output window, and you can very easily monitor the your solution. So what we obtain from each time step is the information about that our time time increment is converged, and this is very good information for us as the FEA analyst. So I'm clicking on the stop button, and I would like to present the results. So I'm going to this empty model, and as you see, all of the time steps, all of the results has been loaded to the model info tree. So I have two subcases. First refers to the free fall, and I have 10 increments as I specified. So let's display the result. We supposed to change the scale of the deformation, so now it's real. And let's play the animation. So this is free fall. And right now, if we select all of the subcases, let's select all, we will display full response. So as the contour, I clicked on the total translation, but let's investigate the stresses. Once again, let's select all of the time steps, and now we can observe the response of our plate. So there is no damping provided on the system, and our material is linear. And at this moment I would like to show you the model which has been calculated before. So if you specify the plastic hardening function, for example, and this is what I'm displaying at this moment, you can investigate this plasticity effects in your analysis. So let's display the results, and now I'm displaying the plastic stresses on the plate. So now we can observe the stresses which are plastic. Yeah? Okay. Okay, so it was an example related to the implicit analysis, and right now I would like to show you two examples which refers to the explicit analysis in terms of quasi-static problems, because there is um, there is a way to handle this type of problems. And from now I would like to give you also some practical advices, and as you know, we can use the explicit code to perform some short event simulations like sheet metal forming or some other impacts. But let's say we can actually, probably at the first glance, the implicit solver is the better choice. We can think like that, but we can perform exactly the same solution via the same class of problems via the explicit, especially for the 3D analysis, where are, let's say, where the explicit solvers are much more efficient. So at this moment, I would like to remind that modeling of the quasi-static events requires some special consideration according to the time duration. So it's very highly impractical to model process in its natural time, which refers to the normal modes analysis, because to analyze the static problem we need a million increments to use in the simulation, and due to this we want to increase the speed of the process in some, let's say, artificial way. And how to do this? So there are two methods. First method to increase the speed of the explicit analysis is to use the proper load rates, and the second is to use the mass scaling. And I didn't mention about the mass scaling because it's quite advanced topic, and this will be considered in the next webinars, but mass scaling allows to you to change and makes the analysis slower. So I will not use the mass scaling at this moment, but I would like to show you some example with the loading rates. And loading rates method will reduce the time scale by, so the goal is to model the process in the shortest time period in which, let's say, the inertia forces will be still insignificant. Okay, so now let's take a look on the example shown on the screen. So we see the two objects. We see the big cylinder, which is impacting a deformable beam. So at this model, the material has been added, and I would like to display the constraints. So this beam is fixed on the both ends, and as the dynamic load, I applied the displacement, and displacement had been provided via the time function. So the value is 0.1, and my time function for this displacement looks like following. So the time is 0.005 second, and the displacement reaches the maximum value. Okay, so this means, if we take a look on the example, that the impact velocity is 200 meters per second, which is very high. And if we play the animation, we see that we receiving the very highly, let's say, deformed shape, and there is no structural response in this system. Let's make it faster, so let's keep some intervals. and now it looks much more better. Okay, so we see that there is a very deformed shape and there is no structural response as we expect to the static or let's say quasi-static simulation. So what we observing is rather than dynamic even than the quasi-static. So how to achieve the structural response? So before I show you the second model, I would like to say a few things about the loading rates, and all we have to do is to assign the proper velocity value to the system. So first of all, you have to perform model analysis. So I will switch the examples to the explicit quasi-static to the second model. So first of all, you have to perform the model analysis and extract the natural frequencies. So usually the first structural mode is the right one, and this will be the dominant response of the system. And as you see, the frequency is 215 Hertz. And next step is the calculation of the, let's say, corresponding time period using this first natural frequency of the model. And after this, we have to estimate the global deflection in impact direction. So when we got them, we can easily calculate the impact velocity from the very simple formula, which is distance divided by time. And a general recommendation is to limit the impact velocity to less than 1% of the speed of the sound in the material. So as you remember from the presentation, for the steels, the speed of the sound is 5,000 meters per second. So our speed in our model should be less than 1%. So 1% is 50 meters per second, and we supposed to model that that system to achieve that value. So according to above considerations, model you see on the screen has been recalculated. So first natural frequency was 250 Hertz, and corresponding time period is 0.0046 seconds, and from this we can calculate the velocity, which is 22 meters per second, and this is valid velocity because it's around 0.5% of the speed. So let's play the animation. Let's select all subcases, change the speed, and let's keep a few increments. Let's click on OK, and let's click play. So you see the deformation looks much more better right now, and the response looks like structural response. So to the end, I just want to say a few things about the suggested approach. So when you want to perform quasi-static simulations via Explicit, you can run a series of simulations in order from the fastest load rate to the slowest, and you also have to perform many simulations to get proper understanding of the effects of varying the model. So that's all for today about the examples. Now let's switch to the presentation, and on this last slide I would like to show you some explicit impact problems. And now I'm playing the animation. So the period for presented event, and right now we are observing the block strike on the propeller. The period for this event is very, very short, and let's say plays important role. And analysis objective for that model, and let's play it again, was to determine the damage caused by rotating turbine due to the impact of the small projectile. So FEA model of that turbine is composed by more than 2,000 play elements, but this is not let's say what I want to tell you, the most impressive thing is that the rotational speed of the propeller is around 30,000 radians per second. So this is very, very high. So you can analyze this type of problems in midas and FX. And the second example refers to the bullet strike on the wall. Now I play the animation. So I would like to also invite you to visit our YouTube channel, Midas and FX channel, to see more interesting videos with other project applications. And at this moment I would like to thank you for your time, and if you have some questions, now there is a good time to do that. Okay, some of you is asking about the automobile body impacts, and the question is, should I follow to implicit analysis? No, as I said, everything depends on the duration of this event. So impact, if you want to analyze the stress wave problems, you're supposed to use the explicit, but if you are analyzing some automotive part like door, and your main focus is to see the deformation, you are not analyzing so detailed what's going on with the propagation of the weight, you can use the implicit analysis. There are also some more advanced questions like damping, relay damping, but this requires more detailed things. So I prefer to, if you can write to us email. The address is piotr.stepian at midasit, or cyprian at midasit.com. So you can use both of these mails and ask us for the more detailed informations. Okay, thank you so much for joining today's webinar, and I hope you enjoyed this session, and very soon we will inform you about the next meetings. Thank you so much. Goodbye.